Okay, so today we're going to be talking about the test, and I thought it would be kind of an interesting exercise to go through some tests that I have accumulated from other classes. So these are not tests that I made, but they go over the same chemistry. So uh, I'm going to show you kind of how I would approach these questions and how I think you guys should. I've got Grace and Marco here to help me out. Hopefully, other people will show up as we go along it. But there's going to be some questions that we can't answer because we have not covered that material, and some questions that um, might be a little bit of a stretch that I might not necessarily put on a test, but that might be good to think through as kind of preparation. So this is naming. I wouldn't get too far away from naming. It's not something I'm going to ask you on this test, but it is something that is fair game for the final. So a lot of these rules are pretty straightforward. Own refers to this ketone. You've got your ene, which is that double bond there. And then the cyclohexyl kind of refers to this with the dimethyl. So you guys can kind of see those parts, but we're not going to spend too much time talking about that today because, well, frankly, it's not going to be on a test. So let's jump straight into the reactions. So this is Dr. Curley's exam from last year. So this is the guy that taught this exact class last year. So we start off with a little bit of a tricky one. So this is what we're given with H plus cat. So this is kind of his notation. This H plus cat is how he would write acids. That's just a general acid for his use. I would typically write H2SO4, or maybe like H3O plus or something, because H plus cat is not something that you can get out of a jar. But we know what acids do, right?
Give protons.
They give protons. But the question is, what do we want to give protons to? Now this is tricky. We're only given one thing. So, the nucleophile and the electrophile are probably going to have to come from the same place. They're probably part of the same molecule, right? That's kind of a hint. I don't have two separate things. I have one. Do I have something in here that looks like a potential nucleophile?
NH2.
This amine, right? That to
Mm-hmm.
me screams nucleophile, right? We've done the chart. Just a reminder, nucleophiles tend to be anything that's negatively charged or something with a metal on it. We have amines, alcohols, sometimes double bonds, where electrophiles, we're really looking at carbocations, carbonyls, and things with leaving groups on them. These are our big picture ones. We can see immediately if I'm looking between this chart that uh, this amine fits pretty nicely here in the nucleophile section. Do I have an electrophile somewhere in this molecule?
Your ketone.
Yeah, this ketone right here, right? Again, fits in the electrophile section. So I've got my nucleophile, I've got my electrophile. Acids tend to protonate electrophiles to make them better. So we're going to see something like this. All right, so this is the tricky bit. Once I've protonated my electrophile, what's going to happen? I do the acid base first, then what happens?
Nucleophile attacks the electrophile.
Right, my nucleophile is going to come all the way around and attack my electrophile. So this is where it's a little tricky, right? Seeing as they're connected to the same line, what's going to form?
A
What has to
ring.
form? I have to form a ring, right? How big
Yeah.
is my ring going to be?
One, two,
I've
four,
got the nitrogen is connected to the
five.
carbon. So I'm going to
Five
go,
carbons, one nitrogen, one oxygen.
is that oxygen going to be inside the ring or outside of the ring?
Outside.
It's going
Yeah,
to be
that was my
outside.
mistake.
So we've got a six-membered ring with nitrogen being one of the members because 6 is binding to 1. I feel like I'm going to lose people immediately here. So 6 binds to 1, so I know I've got
Yeah.
a membered ring before I even have to draw it out.
S- Okay, so 6 is the one connecting the end to 5.
6 is
But what
connecting to 1.
what about right? But
So
then
6 is my nitrogen.
wouldn't right. Okay.
6 is bound to 5, right? Already. 5 is bound to 4. 4 is bound to 3. 3 is bound to 2. And 6 made a bond with 1. So this is my new bond.
Mm-hmm.
So it helps to think to count these through. Like, what is the shortest line between my nucleophile and my electrophile? So then it's really easy. Now that I've got it numbered, I've got the ring. What is on 1? I've got
On
a,
one is going to
Okay,
be a methyl group. Oh, sorry. Yeah, pH.
pH and the electrophile, correct?
and the
Oh
OH,
wait, yeah, you
right?
did it. Yeah, yeah.
Okay. Anything on 2? No.
No.
Anything on 3? I've got these 2 methyl groups. Nothing on 4. On 5, I've got a methyl. Cool. Do you see how we got there? All right. Now I'm going to remember my rules. I've got an amine attacking a carbonyl. We have 2
Mm-hmm.
different kinds of carbonyls. We have the carbonyls with heteroatoms on them. We have the carbonyls with C or H on them. Which world does this one fit into? Does it have a heteroatom off the carbonyl, or is it a carbon? Is it carbons and hydrogens off of it?
Carbons and hydrogens.
Carbons and hydrogens. So I know that when my amine attacks into this carbonyl, I'm going to form an imine, which means ultimately I'm going to kick off that OH and form a double bond. My pH still sitting around. So this is the final answer. I might not be able to say very well. This, right? If you get here, this is probably 3 or 4 out of 5 points. Pretty happy with this. This is for the full credit, remembering that nitrogens adding into carbonyls without heteroatoms form imines. All right, the double bound nitrogen. All right, this is a reaction we didn't go over, so I'm going to skip it. All right. This reaction. Do I have a nucleophile?
Which one? For B?
For B.
I don't see.
No, it doesn't look like it.
Yes.
LAH. What is LAH?
Yeah. Um,
It reduces
How?
it.
the
It turns the carbonyl turns a double bond into a single bond.
How?
from the electrons on the hydrogen.
Yeah, so this is the equivalent of H minus. We've talked about this before. What does that look like?
A nucleophile.
Do I have an electrophile around?
Yes. Ketone.
So this H minus is going to add into the carbonyl. Then H plus quench. I would just write water, but it makes it more direct. And we kind of we get our answer, right? I have I add this H minus into this carbon, and I get the reduced product, right? LAH reduces things. So that's how that works. It's nucleophile electrophile chemistry. All right. It's a little bit crazier looking. But if we follow our rules, we can figure it out. Okay. So, do I have an electrophile anywhere in this picture?
Yes.
Where?
It's the what's that called? An aldehyde?
Yeah, this aldehyde, that's my electrophile, right? Do I have any nucleophiles in this picture?
2 alcohols.
Yeah, so I have two of them. So this is a little tricky. All right, what kind of carbonyl is this? Is it one with a heteroatom off of it or one without a heteroatom off? Heteroatom or no?
Yes, heteroatom.
There's a heteroatom off
Carbon.
this carbonyl?
Oh, no, sorry. No, just a carbon.
It is just a carbon. What happens when an oxygen nucleophile adds into a carbonyl without heteroatom?
It doesn't do that? Or
It does. What does it form?
2 oxygens coming off of the carbon, each with their own R group.
Right, so if we go back, any sort of ketone or aldehyde, if I add ROH, I'm going to get what's called an acetal, where I get two alcohols adding, right, and replacing the original carbonyl. So if we know that that forms an acetal, we know that two of these have to add to form our acetal. What do you think is going to add to form this acetal? What do you think we're going to get here? What's going to happen?
We're gonna have another ring.
Okay, we're going to have to form a ring. Where's my OR here?
Like which alcohol?
it's
Yeah.
Aren't I mean they're the same distance away from the
Right.
aldehyde.
But you see how
So
two alcohol have to add in here? He's kind of giving us a hint. There's two alcohols here.
right.
So what actually ends up happening is that both this guy and this guy add in and you lose water. So we've got to think about this. We've got to kind of draw this carefully. So we're going to number this. Okay. So I've got carbon 1. We're going to imagine this is carbon 1. It's going to be bound to my two alcohols in the new picture. So carbon 1 bound to two alcohols. This is 7. This is 8. Okay, so we're going to probably draw this a little bit ugly. Eight is bound to 5. 5 is bound to 4. 4 is bound to 6, which is bound to 7. Okay, that's kind of weird looking. 1 is also bound to 2, which has two methyls off of it. And 2 is bound to 3, and 3 is bound to 4. Okay, so that's a kind of ugly drawing, but it forms this kind of two-membered ring, or two double cycle. So this is a 1, 2, 3, 4. Oh yeah, you guys can't see this. 1, 2, 3, 4, 5, 6-membered ring. So I'm going to redraw this nice and pretty. It has an oxygen, oxygen. So Dr. Curley liked rings, as you can tell.
Mm-hmm.
So I had a 6-membered ring with 2 oxygens in it. That's this kind of top ring here. Then I have 2 carbons connecting, and this guy's got 2 methyl groups off of him.
I don't like Dr. Curly's ring.
Me neither.
So that's what you're forming. Kind of ugly, but that's the answer.
Very.
So
I
you,
have to do this on the test.
I mean, this is the same course. This isn't anything crazy.
It's just like
Um,
more 3D than something we've done before.
Yeah, honestly, we should have done more ring structures. It seems like it's something that you guys are not that comfortable with. But it's the same chemistry. So you can imagine I could ask the same question just without the ring. The important bit is that you know that this oxygen and this oxygen both add into this carbonyl. That's what I care about. Drawing the ring is fine, but know the chemistry. Know that this carbonyl has no heteroatoms off of it. So when oxygens add in, you're going to add 2 of them. Okay. This is an NMR question. This isn't something we've gotten to. Okay. Now this is something we should be a little bit more comfortable with. So provide a reasonable mechanism for the following transformation. Mechanism being the steps to get from starting point to final product. Okay. We have a nucleophile in this picture.
Is the HNCH3, is that an acid?
That's what that looks like. It's a nitrogen with 2 methyl groups coming off of it and a hydrogen.
That's not an NH2, so no nucleophile.
Okay, so that's kind of where this chart fails. Any sort of nitrogen can be a nucleophile. So R2 and H can also be a nucleophile.
Okay. Okay, so yeah, we do have one.
This is our nucleophile. What is this?
Acid?
Aldehyde.
This is how he writes
Oh.
acid, right? It's just a proton. It's just a proton source is what he's trying to say.
What does cat mean again?
Catalyst.
Kinda.
It's catalyzed by acid. That's what he's trying to say. Do I have an electrophile?
Yes.
Electrophile. Right here. Carbonyl. All right. Do I want to protonate my electrophile or my nucleophile?
Your electrophile.
Always.
Mhm.
So we're going to protonate the electrophile. Then what's the second step of our mechanisms?
The nucleophile attacks electrophile.
Nucleophile attacks electrophile. Then we need to get rid of water and form an enamine. Okay, where's this water coming from?
The alcohol.
Right, we've got to get rid of this alcohol. So I'm going to take the proton from the nitrogen. We've done this mechanism before, almost exactly. And now I'm going to kick off the water using the amine. And we formed this. What am I missing in this picture?
Yeah, and a charge on N.
Right.
Nitrogen is positively charged.
Right.
So
We can't end there, right? We don't want to end with a positively charged nitrogen. So how do we get it to this product?
Yeah.
you use a hydrogen from the alpha carbon you break that bond and push it up towards the carbon and then push an electron from the double bond into the nitrogen.
Yep. So this is the good old-fashioned enamine formation. It's going to happen anytime when you form that imine, and the imine's got a positive charge. So this should be easy for us. We've done this a bunch. This isn't something we directly talked about in class, but I think is a good question. Which nitrogen, A or B, will be the better nucleophile and attack the carbonyl? I want to hear y'all's answers. Give me some justification. What is a good nucleophile?
We want something that's more negative in a sense, right?
Yeah, something more willing to give away its electrons.
I don't know. I think I wanted to say A because it was closest, but I know like that's not how it works.
That's not how it works.
I feel like it's gonna be B because it's further away from the electrophile.
It has nothing to, I can draw the same picture like this.
Ah. No, because it's another carbon away, I should say.
I feel like it actually is A though, because sterics is the only reason that I think you would need to pick one over the other. And A is connected to a carbon that's in the carbonyl, but there are no hydrogens poking off of it, so there would be less sterics. The B nitrogen is connected to a carbon that has two hydrogens on it, so I feel like that would kind of get in the way.
Okay, so sterics is not the answer. We have a more robust answer.
Oh,
1, 2, 1, 2.
oh, is it resonance? Is
It
it
is
the
resonance.
okay? So it's the A nitrogen because of resonance.
Well, let's think about it. What is resonance? What is resonating here?
Electrons.
How?
They can go from the oxygen double bond up into the oxygen and then from the nitrogen to the bond with the carbon.
Exactly right.
Right.
Okay. So
So
you just disregard sterics because of
Yeah,
resonance. Resonance like takes
Ster
precedence over sterics.
sterics only matters in very extreme circumstances. Like if you've got a ton of carbons around something.
Okay.
I mean the resonance structure here tells you something. What does it tell you about this nitrogen?
that it can be potent, like it can become positive and accept electrons.
I mean, yeah, is this nitrogen, this nitrogen's got some positive charge to it, right?
Yeah, which would make it less of a nucleophile.
Right, this lone pair's tied up, we'd say it's tied up in resonance, right? This lone pair's not free as this lone pair. That's just hanging out here. So which lone pair would be more available to do attack?
B.
B, because it's not tied up in resonance.
Got it. So its electrons are not gonna move as easily as A's electrons are gonna in resonance.
Right, if you see in resonance that this nitrogen actually has a partial positive character, so it's really not a great nucleophile at all.
Okay.
Okay, that makes sense.
Right, this lone pair is not as free. It's getting tied up in resonance compared to this guy, which can go do whatever it wants. So that's a good question. It's not something we directly talked about in class, but it's something that through a little bit of thought, I think is worth talking about. Carbon NMR, we're going to talk about this more after the break. Okay,
Oh,
here's
geez.
here's a synthesis question for you.
Oh.
Let's think about this for a second. How would I approach
Okay.
this question? It's a pretty
What do you,
pretty intense question, but I think we can. How do we start these questions?
I kind of start backwards, looking at your product and like seeing
Okay.
what,
What about the product?
how many, if anything has changed, what bonds have moved.
Okay.
If we
Well,
had to like,
let's map out the carbons. I'm gonna number them. 1, 2, 3, 4, 5, 6, 7. I think that's a great starting point.
yeah,
Where's carbon 1 in the final product?
it's next,
Under the
it's like,
chlorine.
Under the chlorine? This?
Yes.
Not quite. Oh, sorry, you're right.
Mm.
I did it backwards. That makes 2 here. Yeah?
yeah,
Mm-hmm.
Where does 3 have to be?
where, oh,
Let's do a thought experiment. Can we put 6 and 7 here?
no,
No. Why?
because they're tap, mm,
Where would that put 3, 4, 5?
not connected, 3, 4,
Not
and then
connected.
5,
So I cannot put 3, 4, and 5 there. So that means I cannot put 6 and 7 there. So where does 6 and 7 have to go?
right next to where the one carbon is. So like, yep,
And then that leaves what for 3, 4, 5?
3, yep, 4 being in the middle.
Yeah, 4 has to be in the middle. Okay. So, um, let's break this down into a smaller chunk. Okay? I'm gonna break that bond. I know I've got to have something here that I can turn into a chlorine. And I've got to have this little carbon unit. So my first thought, whenever it comes to making a carbon-carbon bond, is what?
Grignards.
Grignards. So with a Grignard, I need 2 pieces. One MgBr and one what else?
Carbonyl.
A carbonyl. Period. End of story. And you'll see when I bring these 2 things together, I end up forming something that looks like this. Okay. Always, you're gonna Grignard plus carbonyl, and you get this nice little OH. So where do I want my OH to be in this picture?
6 and 7. No, you want it to be chlorine.
I
Where the
want
chlorine
it,
is.
I can turn an OH into a chlorine eventually, right? So if I
Yeah.
can put the OH at the right spot, which is this X, well then I'm gonna be set up pretty well to put a chlorine on. So what does this mean that the X had to have been?
BR?
If
No.
we're looking at a Grignard.
Oh,
Wait, what was the question again?
if oh, where's the X?
Okay, so the X is where the chlorine was, right?
Okay.
If I want to turn an OH into the chlorine, right? Where I put the heteroatom matters. What side started, did the carbonyl or the Grignard end up with the OH? I need to make one of these a carbonyl and one of them a Grignard. Where does the OH end up?
Where like the chlorine is in the end product, but
Right. So where the chlorine is, where the heteroatom is, needs to be my carbonyl side or my Grignard side.
Grignard.
Where this OH ended up, was that on my carbonyl side or my Grignard side?
Oh, carbonyl then?
Yes, it has to be carbonyl,
Oh,
right? Put the heteroatom where you want the heteroatom to be. Does that make sense?
a little bit. I need a second to see.
It's kind of a weird thing to grasp, but once you get it, you get it.
If you
Wherever
put
wherever the carbonyl is, right? The carbonyl has this heteroatom, has the oxygen on it. If I look at my final product, I'm making this bond.
Wait,
Does
Kevin, are you writing stuff?
am I frozen?
You might be, unless I can't see it.
I can
Marcos,
see
can you
it.
see? Oh wait, never mind.
Okay. Does the left side of this bond or the right side of this bond end up with my heteroatom?
The left side.
The left side. So the carbonyl is the side with the heteroatom. Does that make sense?
Yeah.
That means the other side has to be what?
The MGBR.
So when I put these two things together, what am I going to get? Something that looks like this. Can I turn this into this?
Yeah. HCl.
Yeah.
Sure, HCl. Cool. That's easy, right? Can we
Yeah.
make this? Can we make this part?
Yeah.
From 1, 2, or 3?
You definitely have to have one. It's got the
Have to use
pH on
1.
it.
Yep. How do we make this part from 1?
You would do the anti-Markovnikov of HBr first.
Yep. Put the Br on the outside.
Yeah. And then you would do the NaOH. And then after that, PCC.
Right. You see these same steps over and over. It might seem complicated, but anti-Markovnikov, do a substitution, then you oxidize. So I've got this piece. I'm good to go. Now the question is, how do I make this piece?
You can use both of what you have. I mean, yeah, because you're gonna have to use both. The OH and the double bond.
Yeah, so I'm going to have to use both starting materials. So I'm going back. I'm imagining this Br was here. Yeah?
Yeah.
So what new bond do I have to make? Let's remap. This, remember, this was 6 and 7, and then 3, 4, 5. What's my new bond? Between what numbers?
6 and 7. Oh, 7 and 4.
6 and 7 were already together. 7 and 4. That's my new bond I have to make. Yeah?
Yeah.
Okay. Where's the heteroatom on either side of this bond? The left
Left side.
side or the right side? So that means my left side had to start out with what?
A heteroatom to begin with.
Okay, so is that my carbonyl side or my Grignard side? I'm making a carbon-carbon bond.
Carbonyl.
So my left side had to have been my carbonyl side because it is the side that ends up with the heteroatom. Yes?
Yes.
That means my right side had to be what?
Grignard.
Grignard. Where? Where's my Grignard? 3, 4, or 5?
Or
Cool. These two things together make this. Can I turn this to this?
HBr.
Can I turn this to this?
Yeah. Mg.
Mg. Can I turn this to this?
Yeah.
How?
That.
HBr
Yeah.
and then Mg.
Can I turn this to this?
Yeah, but that's where I'm confused.
So I need to put OH on it. So I'm
Oh,
just gonna do
NaOH.
Oh, and
H2.
then you just
Oh.
oxidize again?
Oh, I don't like that.
You do not like that?
No, that's some practice I need then.
Yeah,
Okie dokie. Yeah, I was gonna ask about it.
this is a pretty complicated one, but it's something that could be fair game for the test. But on Friday morning, we're gonna
Yeah.
practice. We're gonna start from a more basic. There are a lot more basic examples on your lecture notes, so we'll try those. And honestly, it's just pattern recognition, right?
Yeah.
I make a carbon-carbon bond, I think, well, I've got to go back to Grignard, most likely. Then you
That
see,
definitely helps.
where's the heteroatom? The side with the heteroatom had to have been the carbonyl side. So, CC bond, go to Grignard. Heteroatom side, that's your carbonyl side. Cool. We can build some pretty big structures out of that.
Yeah.
All right. Let's do a new one. All right, this is the next exam. Skipping the naming. Okay. So, this is a good question. The reaction below will not give the product shown. What will happen?
OH has to add into the carbonyl.
What kind of catalyst do we have?
A
A
base.
base.
What is this basic catalyst gonna do?
Oh, it's
It's
gonna
gonna-
deprotonate the alcohol.
Yeah, it could
Yes.
deprotonate this alcohol, definitely. And that would be ideal. But what's the problem with that?
You lose your nucleophile.
No, you would make a great nucleophile. This would be a great nucleophile if you're able to do this.
Oh.
But you're not able to do this. Why?
I don't know.
What is this?
Electrophile. Carbonyl.
What kind of carbonyl?
Carboxylic
Carboxyl.
acid.
What do carboxylic
Yes.
acids do?
They protonate things.
Okay, so if I have a base and a carboxylic acid, what's gonna happen?
It doesn't.
They will react.
See this?
Mhm.
This is a terrible electrophile.
Yeah.
Why?
It's like almost combining both electrophile and nucleophile.
Right, it's
Just like-
literally negatively charged. It does not want any more electrons.
Yeah.
So you got to be careful with this, right? The kind of catalyst matters because in this case, a base would deprotonate my electrophile, and that's a bad thing, right? It would ruin my electrophile. So that's what he's trying to get you to see here. So if I wanted to get this reaction to go, what should I add instead?
An acid.
If I had an acid here,
Okay.
well, now I don't have to worry about deprotonating things. I can protonate my electrophile, and we would be good to go.
And they can carry out.
Yep, and then we're eventually going to get there, right? Because this is a carbonyl with a heteroatom, we're going to do a substitution on it, right? So we have a carbonyl with a heteroatom on it. We add some nucleophile. You're just going to sub out that heteroatom for the new nucleophile. So we're kind of combining these two tests because of the hurricane thing, but his were two separate tests. All right, this is something we talked about today. This was new material.
Oh.
All right. Do I have any electrophiles in this picture?
What is an aldol again? We just did that in class.
We did. Don't worry about it. Do I have any electrophiles in this picture?
Yes. You
Where?
could. You could have two.
Yeah, I have two things that kind of look like electrophiles, but I don't have anything
Right.
that looks like a nucleophile. Yeah.
Right.
So now I'm spinning. What do I do?
Make something a nucleophile.
Make something a nucleophile. What is that?
Base.
A base. Do I have any acidic protons in this picture?
A few of them.
Yeah. Which ones?
All of the hydrogens that come off of the alpha carbons.
Right. So I'm looking one carbon away from each one of these carbonyls. Is this acidic?
No.
No, don't fall into that trap. One carbon away. Alpha carbons. So I have here, here, here. Three different spots I could potentially form alpha carbon for. He's given us a product. What does this product look like?
It looks like that they made this second electrophile a nucleophile and kept the first one
Right.
intact.
So most likely this is going to be my nucleophile, and we'll kind of talk about how we got there in a second. But you can see, let's map this out, right? Whenever we're lost, map out the carbons. 1, 2, 3, 4, 5 with a pH. 1, 2, 3. So we have 1, 2, 3, 4, 5. 1, 2, 3. So this is the new bond.
Mm-hmm.
So that new bond is touching carbon 5 and carbon 1. What's on carbon 1?
Nothing.
One hydrogen.
It's my carbonyl, right? This is my electrophile.
Oh, I was looking at the product.
What's
Yeah.
carbon 5?
Carbon 5 is bonded to it, and it's got two hydrogens on it.
Somehow 5 has to bond with 1.
Yeah.
Could 1 possibly be a nucleophile?
Yeah.
Carbon 1 can? How? Does it have an alpha proton?
Oh, wait, no.
No. Does 5 have an alpha proton I could take?
Yeah.
Yes.
So which alpha proton do I need to take to get to this final product?
The one off of carbon 5.
I need to take this alpha proton because it is the one on 5. Okay. I've formed my nucleophile. What happens?
It's gonna attack the electrophile.
Gonna attack the carbonyl.
All right, that wasn't that bad. Oh wait, you're not done yet. You're not done.
All
Okay.
right. I'm gonna quench it and we form this. All right. Is this the same as this?
No,
No, what's the difference?
you need a double bond.
I need to get rid of something and replace it with a double bond. What do I call that? What kind of reaction is that?
Oxidation.
Oh,
No. I'm literally removing something.
Elimination.
there you go. That's
It's
the
an
word.
elimination, yeah? In order to form this double bond, I need to get rid of two things, right? Because a double bond goes across two different carbons. I need to get rid of the OH on this carbon, but that's still, this carbon already has four bonds. So what do I have to get rid of? What else do I have to get rid of in order to make this double bond? That looks like a triple bond. How do I do an elimination? Actually, we don't even need to use that language. How do you, what mechanism gets you from here to here? How do I justify this?
Adding heat.
Okay, adding heat, but what are the arrows? What are the mechanistic arrows? What's going to happen?
What's that? It's gonna be adding electrons.
Would a
I
water come in and take a hydrogen? I'm so sorry, Grace.
no, you're good. Go. You're good.
Which hydrogen?
Um, the one that is on pH.
You mean this guy?
Yeah.
Right. In order to form this double bond, I need to take something from each side of the double bond, right?
So you would,
I take this hydrogen, it gives its electrons to make this double bond, and I kick off that OH. Another way to think about it is how many hydrogens are on this carbon in this picture?
Which one?
The one in gold.
Oh, just one.
How many hydrogens are on it in this picture?
Which picture? Oh, zero.
So I had to remove a hydrogen. This is a very common elimination, right? You take a proton from the neighboring thing, you get this. The mechanism we went over today. This first step is straightforward. It's just doing the elimination at the end. That could be a little bit.
So
Okay.
what like sets this apart from stuff that we've done in the past? It seems familiar. I just don't know if like I'm supposed to pick up.
It's the same stuff. Nucleophile attack
It's the
electrophile.
same. Okay.
Yep.
Okay, which is like more like work at the end.
Right. We're just taking it one step further. So
Okay.
yeah, that's
Got
why
it.
you guys knew the first two steps of all of these reactions for the whole semester at the first test. Now we're just kind of adding what happens after that.
I have a question.
What's up?
For the OH to leave, it doesn't have to be water first.
No, because we're in basic conditions,
Okay.
it does not have to be, but it usually does. So
Okay.
it's a little confusing, but yeah. That's a good question. That's a really good question. But you think about it, you're just kind of switching. There's excess OH, minus, and so you're just kind of switching one OH minus for the other OH minus. So it's kind of a net neutral.
Okay, thank you.
Okay, so this is kind of something that we didn't talk about much today, but it's something that's worth thinking about. What's going to happen here? Step one, I've got a base and I've got this carbonyl. What's going to happen? Do I have an acidic proton anywhere?
Yes,
Where?
off of the pH where it meets the O, like that carbon in the middle.
The
This
other
one?
carbon.
No.
There are no hydrogens on that carbon.
There's
It's the
no
other carbon.
hydrogens here
Oh.
because it's a phenyl, it's a benzene ring. Do I have any hydrogens
What
over
a
here?
shame.
Yeah, you do have, you have three there. Yeah,
So do I have an acidic hydrogen? Do I have any alpha hydrogens?
Yes.
Yeah, I have
three.
one right here. So
Okay.
I've got a base, it's gonna take it. So I'm gonna form this. Do I have this is a good what?
Nucleophile.
It's a good nucleophile.
So what happens when I pair it with, say, an electrophile?
It'll react. The nucleophile will attack.
I get this.
Okay, this is like the only simple one so far.
So the thing is, the following reaction will not give the product shown.
Mm.
But that's what we're predicting we get. What's wrong with this picture? Why is this not the complete picture?
You didn't,
It was step 2.
What if I wrote it like that?
Then that'd be correct. Hmm.
Pretend I have excess of both. What could happen if I have more of this sitting around?
you would deprotonate the alpha. Yeah, you do that again. And you could stack on a bunch of little carbon chains.
Yeah, you could do the exact same reaction again. And you do this.
Can you
And
do that
then
one more time as well?
you could do it one more time. So, I don't teach it this way because I don't know how actually accurate it is, but Dr. Curley taught it like this, that you in theory could keep going. I'm happy with this answer. His solution is to use LDA to stop at 1. I don't know how realistic that is. But I'm cool with both. I'm not going to ask you this. If you give me this as an answer, I'm not going to be upset about it. I'll give you full credit. But he taught that LDA stopped at 1, where OH kept going. But you can see theoretically it could keep going no matter what the base is. So this is another problem with enolate chemistry potentially, is that you can keep taking alpha protons.
Didn't you say LDA was a base?
Yeah. So it's lithium
Diamide.
diisopropyl
Oh,
amide. That's what it looks like. It's a bulky base, right? Whereas OH is not a bulky base. This one has all these carbons coming off of it. It makes it bulky. So I think that's his argument, that a bulky base would be less likely to take a second proton. But it is what it is. Okay, I'm not too worried about it. I just want you guys to see, hey, sometimes there's more than one alpha proton. It could keep going, but that's not necessarily a question I would ask you guys. All right. Now we're getting into just fill in the blank. I have a nucleophile here? We haven't covered this directly, but do I have a nucleophile here?
I mean, you have a lot of double bonds. Those are one of our nucleophiles.
Okay. Do I have anything else that's just screaming out to me?
Copper, lithium,
Yeah, what is copper?
a metal.
So that means whatever it's attached to is what?
Leaving.
Negatively charged.
Which makes it good what? Have we forgot our nucleophile chart already?
No.
Begin. What's on the nucleophile chart?
Negative charge
How do we often hide a negative charge?
with a metal.
Metal.
So both of those two carbons connected to the copper are nucleophiles.
Yes. Nucleophilic carbons, because they're attached to a metal. That should, first thing you're looking for is a metal. First
Okay.
thing. This is a nucleophile. To have an electrophile in the picture.
Your carbonyl.
It's carbonyl. And this actually kind of does something funny. We haven't talked about this yet. We will talk about this when we get back. But these actually end up attacking into this carbon, pushing all the way up into the carbonyl. We'll talk about that we'll talk about that after the test. But instead of adding into this carbonyl, it adds into that carbon and pushes up into the carbonyl. But it's the same idea. But even if you weren't able to get this, I would hope you would see that there's a nucleophile because there's a metal here. I have a carbonyl, that's an electrophile. All right. Do we have a nucleophile?
An H2,
Do we have an electrophile?
carbonyl.
We have an acid. All right. I have a carbonyl, that's an electrophile. Question one, does it have a heteroatom coming off of it?
Your electrophile?
Does my carbonyl have a heteroatom coming off of it?
Yeah, oxygen.
Right. Remember we said if there's a heteroatom coming off our carbonyl, we're going to replace it. We're going to substitute it with a nucleophile. Yes?
Yes.
Easy rule. So I have this. What am I going to replace?
Your oxygen.
What am I going to replace it with?
NH2.
Not NH2, but NH because we're going to make it neutral. We're going to remove one of the protons. Okay. Is this it?
You left out a couple carbons that were part of the chain.
So don't forget these two carbons. Well, just because I'm replacing this, is that O still attached to 2?
Yeah.
Yes. So I'm going to make an OH to make it neutral. This is just like something on the quiz.
This
You
is
see
where
it?
I get confused though, because sorry,
No.
if you're taking NH2 and you're attacking the double bonded O, wouldn't the NH2 be coming out of the same place as the double bond? Why is
Right
it
here.
going to a whole, like,
Right here.
wouldn't it though be coming out right where the double bond is, like that carbon?
This nitrogen bonds to this carbon.
Right. In your product, it bonds to it. Wouldn't it be coming out of that same carbon?
It is coming out of the same carbon. I'm confused.
Okay, I mean more of like this. I know it's breaking out tet, but just give me a second. Like this is, oh, let me embroider this. This is what I was thinking. I know it's breaking out tet. You would move the double bond and, but I'm thinking it would be coming out of that.
So what you've drawn is one of the intermediates where we're going to have, well, it's almost one of the intermediates. So you've got to push the carbonyl electrons
Right.
up.
And then,
Well, actually, we protonate it first. It's not that big of a deal. But, yeah,
see, like
then
that's what,
this guy's going to come back down and kick off this oxygen. And that gets you here.
okay. Okay.
It's one of those things where it's like I can justify this to you,
Mm.
because if we were to do any other combination, we'd get something like we had a similar question on the quiz
Mm.
where a lot of people gave me this because instead of doing this, they kicked off this OH. But this is way more stable than this. So we observe this product. So it's one of those where you almost have to know the product and you can kind of work your way back
Okay.
to determine like, because yeah, in theory, I've got this carbon and I can have all sorts of shenanigans. How do
Right.
I know which heteroatom gets kicked off? How do I know which direction all these arrows go? Well, if you can just think about it as a substitution, and then you can kind of work your way to it on the mechanism. That's the best way I would encourage you to do it.
Okay.
We know it's going to substitute straight up. So this will give you most credit, but it's not the right answer, so we're not going to waste time on it. Okay. This is an interesting question. Lithium aluminum deuteride. What is this?
LAD.
Yeah, what is LAD? What does it look like?
Would it react like Li aluminum like H4?
Yeah, so if we've got LAH, lithium aluminum hydride, what does this act like?
A base.
Not quite.
It acts like a nucleophile, right?
How'd you know?
Because it's a negatively charged hydrogen.
Right, I have something attached to a metal. Red flag. That means the thing attached to the metal is what?
A
It's got a
nucleophile.
negative charge.
It's got a negative charge, which makes it nucleophilic. What's attached to a metal here?
D.
Whatever D is. So I've got a D minus. This is deuterium. This is actually, it's just a heavy hydrogen, is what it is. I haven't taught you this, but you guys should know the answer. What is this? Nucleophile, electrophile.
Nucleophile.
Nucleophile.
Do I have an electrophile in the picture?
Yep.
Yeah? What's gonna happen?
It's gonna attack electric file.
I broke a carbonyl. What does it want to do?
It wants to reform.
It wants to reform. Can I make room to let it reform? Is there anything I can kick off?
Yeah.
What?
Your O ethyl.
Any heteroatom. In this case, oh, I lost carbon. Let's say I have more of this sitting around. This is a what?
Still a nucleophile.
Base.
What is this?
An electrophile.
What can happen?
Attack. But then you're left again at the same.
I broke a carbonyl. Can it reform?
Yeah.
How? What could I kick off?
One of the D's. No.
No, the D's
pH.
are like hydrogens, so you can't kick them off. So I'm
pH.
stuck here. No, you can't. It's
Oh,
got to be a
you
heteroatom.
would
It's got to
just
be
leave it.
oxygen or nitrogen or a chlorine or a bromine. So I'm
You
Okay,
stuck
just need to
so
neutralize the oxygen now, right?
but can
and
water?
neutralize. Yeah, with this H plus, which is what he gives us.
Okay.
So that's the answer.
What is he trying to signify by quench?
I've got this negatively charged thing. I'm gonna quench it. I'm just gonna give it a
Like
proton.
hydrate it?
Yeah.
Like think of drinking water.
It's like me saying I put H2O usually here, but he puts H plus quench. Like, hey, this just takes a proton. We haven't talked about Claisen condensation, so I'm gonna skip this one. But we have talked about this.
That's from today's stuff.
Yeah. So this is an aldol. I've got an OH. I've got a base. What do bases do?
Except
They accept protons, right?
Yeah.
In this case, do I have any nucleophiles?
No.
Nothing immediately stands out. Do I have electrophiles?
Yes. Two.
I have two carbonyls. But we learned today that we can turn a carbonyl into a nucleophile. How?
By moving the double bond.
No. What did we do up here? What does a base do?
It would be by
Oh,
deprotonating it.
We deprotonate, right? We deprotonate what?
A heteroatom.
Well, none of the heteroatoms in this picture have
An
protons.
alpha carbon, I mean, so
An alpha proton, right? So those are protons one carbon away from a carbonyl. So if we take this alpha proton, let's imagine that. Is there an electrophile nearby?
yes.
Let's think. That makes a 1, 2, 3, 4, 5, 6 membered bond. Membered ring. That's totally possible. Here's another alpha proton. Can it come? If we did that, it would make a 1, 2, 3, 4, 5, 6 membered ring. This is actually what he wants. I don't know why he gave you two options. But what we're trying to do is form this enolate. It adds into this. And we form this 6 membered ring. We form this. And then we're going to protonate it. So this is just a pretty standard aldol where he gave you two options and he kind of suggested this just based off how it was drawn, that this is the reaction that makes sense. But it's the same thing we've been doing. You remove one of the alpha protons, then it adds in and it forms a ring. This is stuff that we haven't gone over. Okay.
Can you go back up for a quick second? Sorry. Just so I can take a picture.
Yeah, and I can post these PDFs online too.
Oh, okay. Thank you.
All right, synthesis. So this one's a little tricky. He added an extra layer. You can have any one carbon molecules plus these. So what's step one with these questions? And you guys aren't making good video product.
I'm sorry.
Sorry.
Scary problem.
Yeah,
Step
that's
one, start it. Step
got a lot
one.
of baggage.
Mhm.
Okay, step one, let's look at our end product, see how we got there.
Okay.
What changed? Okay, from there, let's number our carbons. But we can't even because
No,
Yeah.
for the end product carbons.
Okay, let's try to map these starting products on the end product. Okay,
Okay.
Yeah.
where does
Yes.
one have to be?
next to the pH on one side and the other.
So I have two different forms of this. So I'm going to need this at least times two.
Yes.
That's fine. Okay. Okay, this one's a little
Okay.
tricky.
Okay, ready?
You see where 2, 3, 4 could be.
Yes. Okay, 3 is next to 1. 2 is on the end. And 4 is up top.
Okay, and then here's the messy bit.
Okay.
How many carbons do I have left?
1, 2, 3, 4.
And this only has 3 carbons in it.
Right.
So I'm just going to say 2, 3, 4. Okay, so this goes into another level past this. This is the next test. So I'm going to look kind of towards the middle. If I could break these into 2 smaller chunks, that's going to work for me. I'm going to look for the heteroatoms. Eyes go to the heteroatoms.
Mhm.
Can I form this bond?
Yeah, you can.
How? What 2 pieces would form that bond? I'm going to write all the carbons out.
MGBR.
Okay,
And
so what kind of bond is this? Between what 2 atoms?
a heteroatom.
What 2 atoms? A bond is between 2 atoms.
Like oxygen and carbon.
Right. Grignards make what kind of bond?
Carbon, carbon.
Is this a carbon-carbon bond?
No.
No.
No. What kind of bond is this?
Carbonyl.
Carbon.
The carbon-oxygen. Yeah?
Oh, yeah.
So, um, so Grignard's not going to be helpful for a carbon-oxygen bond. Okay? Do we have any reactions that, well, okay. I'm gonna just go ahead and tell you guys this one. Mr. Hydrogen. Okay. These two things together will get you this product. How do I know that?
Your alcohol on the left will add into the carbonyl.
And because it's got a heteroatom, it does a substitution of it.
Mm-hmm.
So I've formed an ester. This is a very standard ester formation. I've got an alcohol, I've got a carboxylic acid. I can put them together to form this ester. So when you see an ester, if I see an ester in my final product, I'm going to go backwards and see that I started with a carboxylic acid and an alcohol. Pretty standard. Every time you see an ester. So when we need to make carbon-carbon bonds, we look at Grignard. When we need to make an ester, we're going to look at this esterification is what it's called. Okay, I'm going to start with the easier side. I'm going to break this into smaller chunks. We established that this is 1, 2, 3, 4, right? So what's the bond I need to make?
Between 4 and 2.
I think 1 and
Mm.
3.
Between 1 and 3.
Oh,
4 and 2 are already
Yeah.
part of the same, right?
yes.
So
I was
that
looking at
means,
the product.
no, you're good. That means I need pH with carbon 1, and I need do. Oh, this goes into something else. So the heteroatoms on this side, okay. This goes one step further. I'm gonna skip this problem. This is a
Yeah.
problem I do want you guys to be able to do, but we need to talk about it kind of more specifically on Friday. So what this actually is going to be that this is enolate stuff. Because if I look at the squiggle, if I look at this bond I broke, the heteroatom is not attached directly to the bond. It is one carbon away, which means I cannot use my Grignard. I have to use the enolate chemistry for this. We'll get more practice doing that. Yeah, I think I'm going to skip the rest of this problem.
Have we learned phenolate chemistry?
Enolate chemistry?
Yeah, isn't that what you just said?
Yeah, this is what we did today.
I knew that.
Okay. So the trick with this one is that it's a Grignard with CO2. I've made a whole worksheet that walks you through synthesis. So I'm gonna post that after this. And I want you guys to practice. I'll post it. It was when I taught for this guy, I made a whole kind of tutorial worksheet that goes step by step through this. So hopefully that will help you guys. I'll post that later today. Okay.
Perfect.
Import.
All right. I have to get going, but thanks very much. Oh wait,
Yeah.
you're going over. Oh, have so much fun with this. But you're uploading this on Canvas?
I'll put the video on YouTube, and I'll put these tests that I've put the answers on. I'll put these sheets up on Canvas and the practice synthesis stuff on Canvas. But I have this is my last test I want to go through. You guys don't have to stay. I'm just going to keep going. This is actually a full organic 2 class. This is
Oh,
when I taught organic 2 last, well, not last, a couple years ago. This is his test 2. So it kind of overlaps with what we're talking about, and you guys can kind of see what the difference between this class and a full class is.
thank you, Kevin.
Yep. All right, Grace is leaving. That means I need Evelyn and Kaylin to step in and be more vocal.
Okay.
Yeah.
Okay. Question 1. Which is the electrophile, which is the nucleophile?
The electrophile is the carbon dioxide and the MGBR is the Grignard is the nucleophile.
Always. That should be easy points. Yeah? Okay. What gets oxidized and what gets reduced? Or what is the oxidant? What is the reducing agent? What thing is doing the oxidizing?
The OSO4.
Yeah, that's pretty straightforward, right? It's a thing with all the oxygens on it. What is doing the reducing?
The water.
Yeah, so let's yeah, you are right. This is the reducing agent. This one's neither. So what is the electrophile?
The first one. With the
Carbonyl?
carbon.
Electrophile. Easy. What is the nucleophile? Only other. All right. pKa's. I don't know why he's doing pKa's this late in the semester, but pKa's. Which one is well, let's not worry about it. Let's save our time. It's about acidity. The throwback. Um yeah, again, something that we didn't really talk about directly, but kind of is, not bad to talk about. Um so when we're thinking about least reactive to most reactive in acyl transfer reactions, we're looking at the electrophilicity of these carbons. Which one's going to be most electrophilic? One, or I guess 1, 2, or 3, and why?
I think 3 because there's a leaving group.
Yeah, this is the best leaving group, right? It's also the most electron withdrawing, which makes this more positive. So because of that, this is the most reactive. What is the second most reactive?
Is it 2?
2, right? This one's less electronegative, but it's still a better leaving group than 1. So this is just a periodic trend where this being a great leaving group, this being an okay leaving group, this being a bad leaving group makes this trend happen. Okay. What is NABD4?
A base. Or an acid, I mean.
Okay, what makes you say that?
That the Na is stabilizing the charge of whatever D is. Or BD is.
Okay, so what is B?
Boron.
Boron, right? That's a metal. Sodium's a metal.
And it's
Yes.
stabilizing whatever D is, which I don't know.
What are things attached to a metal?
Nucleophilic.
Yeah, so what's nucleophilic in this case?
1,
D.
yeah, D.
So I have a negatively charged D. What's gonna happen?
It's gonna.
It's oh, sorry.
No, you're good. We're both saying the same thing.
Then what happens? I broke a carbonyl. It wants to reform, can it? Are there any heteroatoms to kick off?
Yeah, I can kick off the hydrogen, right?
No, that's not a very good leaving group. That's a terrible leaving group, actually.
Then can I kick off the benzene?
Nope, it's got to be a heteroatom.
That's yeah, those are carbons.
So
So
it's stuck like this. So what do I do with the negative charge?
You take one of the hydrogens from the second step, or you
All right.
take the only hydrogen, I guess.
Yep. A very similar question to what we saw in the last test with LAD. This is just sodium borodeuteride. It does the same thing.
So is D like if this like the same thing like when we write R in your class?
No, D is actually it's a heavy hydrogen.
Oh, okay.
So it's just a hydrogen atom with an extra uh, neutron.
Okay, gotcha.
So it's interchangeable with a hydrogen.
That's why you can't kick it off. Got it.
If I've got 10% battery remaining. All right. Do we have a nucleophile?
Yes.
What is it?
The alcohol.
Do we have an electrophile?
Yeah, the carbonyls.
I have two, but they're identical. So what's going to happen?
The alcohol is gonna attack the carbonyl.
Does this carbonyl have a heteroatom on it?
Yes.
Yes. What does that mean? My carbonyl's got a heteroatom. What am I going to do?
Substitution.
I'm going to substitute it out. So what am I substituting out?
The oxygen connected to the carbonyl.
So you end up actually making this. So I substitute that out. So it's connected to this, this, and this.
And a hydrogen, right?
What do you mean?
Or does the hydrogen, the OH on the nucleophile, that does that leave in the process of them bonding?
Yeah, you need to get it to leave to get this. You're gonna depronate it eventually.
Okay.
Yeah. So what is left over here? We have this, and then this oxygen, and it says it's a carboxylic acid. So this is actually where that proton goes. This is our carboxylic acid. Do you guys see that?
Mm-hmm.
Was this jump reasonable? Did I jump too far here to just substitute this O for this O?
Yeah, that makes sense.
Okay, cool. We didn't learn about this, but we can kind of guess what it is. This is an epoxide, so this is actually very equivalent to a carbonyl, where if something adds, it opens up like this. So it's a good electrophile. Do I have a nucleophile in this picture?
The CN, the
How do you know
nitrogen.
CN is a nucleophile?
It's connected to a metal.
Yep. So what's going to happen?
CN jumps in and bonds to one of the carbons.
Would the oxygen not go and grab the acid first? Like the hydrogen first?
It's second. It's listed as the second thing. So it takes it after the addition. Does that make sense? I mean, you guys haven't seen this before, but I think it's pretty straightforward. All right, I have a nucleophile.
Nitrogen,
I have an electrophile.
carbonyl.
Does this carbonyl have a heteroatom on it or not?
Yeah.
Yes. So that means I'm doing what?
Substitution.
Done. Substitute this in, out for the Cl. It deprotonates the N, that H goes here, the Cl. Done. Okay, so this one's a little tricky because I haven't taught you this. But if I've got a carbonyl and I add alcohol, what's going to happen?
It's gonna give you like an X shape with two oxygens at the top.
Yep. This process was reversible. If you add H3O plus, so acidic water, you can get it to go back, right? Where this oxygen becomes, the water oxygen becomes the carbonyl oxygen. So this is a reversible process. You can see here, yeah, that X shape that you're talking about with the acetal. So that tells me that if I see these, I'm going to try to color code this. That carbon that's connected to the two oxygens, well, that used to be my ketone carbon. Right, if I map it out onto this picture up here. So anytime I see two different oxygens connected to one carbon, that's a good sign that I did an acetal formation. What am I missing? What had to, what? 3 carbons, right? 1, 2, 3. And then what's on those 3 carbons?
In alcohol.
Just one?
Does it matter?
Is there an alcohol on both sides?
Yeah, so let's think about this. If this was our product, we would have to get this. Oh, that's ugly. We'd have to do this to get 2 additions in there. Is that what we want?
No.
No, we want both oxygens to have been part of the same chain. So you guys see how, like, if I break those 2 bonds, I get this?
Yeah.
Right, it's my 2 pieces. I know it's kind of hard to see with how much I've drawn all over it. But if I make these cuts, you can see where the ketone and the alcohol come from. So this is a basic reverse aldol, or acetal formation, where you have 2 alcohols adding in twice. Dr. Curley had a very similar example. Okay. So carboxylic acid and this. So now we're having to think backwards again. So when in doubt, I've got 4 carbons. What have I formed here? What is this? What's the functional group called?
Is that an
Ketone.
ester?
An ester, right? How do I form an ester?
Adding an OH into a carbonyl.
Not just any carbonyl, but a
Oh,
carboxylic acid. So this was my carboxylic acid. Let's see, 1, 2, 3, 4. That had to have been my starting material. We might not make it to this test. But whenever you see an ester formation, we most likely started from an alcohol and an ester. In this case, they have to be on the same ring because the final product has formed a ring. This is kind of the reverse of some of the reactions, the reaction that was on your quiz, actually. All right. What happens with HBr to this?
Markovnikov adds in.
What happens with Mg?
MGBR.
This an electrophile? What's it going to do?
Attacks a carbon, breaks a bond.
That's what the HCl protonates it. So that's what it does. You don't need to know about epoxides, but they work just like carbonyls. So you guys can do all of that. Okay. What is this product? Immediately. What is that functional group?
Amide.
It is an imine. Yeah, how do I get imines?
Adding a NH2 to a carbonyl.
Yeah, if I had a carbonyl and I add an amine. So he gave us one of the two. What is this?
That's NHR2.
Yes. Is this my amine or is this my carbonyl?
Your amine.
It's got to be my amine. That means, so I can map that on here, right? So I formed this bond. What had to be on the other side of that bond? What was the other part?
A ring with a carbonyl on it.
Had to have been. Had to have been, because that's the only way I can form an imine is with a nitrogen and a carbonyl. So that's where my carbonyl had to be. All right, this is a positively charged imine. What am I going to do to it? I'm not happy with it being positively charged, and I can't remove a proton.
Push the bond down and break off a hydrogen from the alpha carbon.
I'm going to form the enamine. Cool. Done this before.
You would form that by the OH taking the hydrogen and then pushing the double bond up, correct?
Yep. Exactly. This isn't a reaction that we've talked about, but essentially heat releases CO2 here. So this is your CO2. Not really going to talk about that in this class. So this is one of the ones where you would just not know if you took Orgo 2. Yeah, here's an interesting question. So it suggests a reasonable mechanism. Well, what bond have I formed?
You added the alcohol into the carbonyl.
I added the alcohol into the carbonyl. And because there's a heteroatom, I replaced it. So what's my nucleophile?
Oxygen, the alcohol,
What's my electrophile?
your carbonyl.
What am I going to do?
You're just replacing the alpha chlorine.
So it's asking for a mechanism. So I need to draw the full thing out. I broke a carbonyl. Can I reform it?
Yeah, you could, but the instead you should kick off the chlorine.
And that gets me to this product. That's something you guys can do. I actually skipped a step. My bad. Um, but we just deprotonate this to get here. It's not a big deal either way. But yeah, we've done this. All right, provide curved arrows to get from here to here. All right, what's lost electrons?
Oxygen.
Oxygen's lost electrons and it's formed a double bond near it. So it had to have pushed electrons down. What new bond have I formed? Well, I mean, this carbon can't have another bond. So I've got to get rid of that double bond. Where am I going to put it?
It bonds with the H and then it kicks off the chlorine.
Yep. We've done these practice problems for a reason all semester. I think it's important. All right. So what happens here? We can kind of look ahead and see this. Do I have a nucleophile?
Alcohol.
I have an alcohol. Do I have an electrophile?
Um, Aldehyde.
Yeah, this looks an awful lot like a carbonyl, doesn't it? What's going to happen?
Alcohol adds in and bond pushes back up.
Then how do I get from here to here?
The chlorine steals the hydrogen.
Yeah. All right. So all the rest of this, I mean, honestly, I think this test is easier than the curly tests. I think you guys should be able to get an 80 plus on this test. The class average for this test was a 50, by the way, for full organic 2 students. So if you feel like you could do better than a 50, then you're doing great. All right. Cyclopentanol. I'm at 1%, so this is about to die. But this is kind of harder. This is cyclopentanol. So you can kind of map that out here and see kind of where you would had needed to do something here. This is kind of different from how we structure our synthesis questions, but you can see the main thing I want to point you guys to is like here. That is a carbon-carbon bond with a heteroatom. So what had to have been before this?
It would have had to be a Grignard, right?
Yeah, so the Grignard would have looked something like this. And my iPad died. So yeah, I just want to show you guys like if we can approach this stuff logically, step by step, where's the nucleophile, where's the electrophile, put them together. Then we remember our little rules about is there a carbonyl, is there a heteroatom next to the carbonyl or not? Then we can kind of approach these things logically and not get too overwhelmed. I think acetals tend to confuse people a lot. So I'd look at acetal chemistry. You can see that they often form these weird ring structures. So I think that's worth practicing. Amines, enamines can confuse people. and then getting kind of imine stuff confused with replacing heterocycles on carbonyls. But I mean, if you just, I think you guys are fine. You just sat here for 2 hours with me going through this stuff. So I hope this was helpful. Do you guys feel like it was?
Yeah, for sure.
Yeah, it was
I
helpful.
agree.
Okay, so I'll post this. I'll post the blank tests and the answer sheets that we went over. Um, wait, I could have been charging my iPad this whole time. I'll post that, and I'll also post the step-by-step worksheet for synthesis practice. So that should help you out too. Yeah. Do you guys have any more questions I can talk about for the next 5 minutes, or are we good to go?
I was like, I don't know if this is like a lot to ask, but I was wondering for the World of Carbonyls worksheet, like some of, I don't, that one really confused me. And like the answer sheet, usually I can look at them and like it helps, but I didn't really like, I feel like a lot of it is like jumbled around. So like I was wondering if you could just like go through and like tell me when each one like cuts off or like some.
The first one or the second one?
I don't. I didn't see the second one. The one, if it was the one we did on class on Friday, then I missed that one. So I'm assuming, I guess, Wednesdays. Lecture 27.
Okay, here. We've got this right here. Can you guys see this?
Yeah.
All right. So let's go to the practice. All right, nucleophile,
The NH2,
electrophile.
the carbonyl.
Is there a heteroatom off this electrophile?
Um, no.
No.
Carbon, carbon. So no. Easy no. So if it's a nitrogen nucleophile adding into a carbonyl without any heterocycles, what is it gonna any heteroatoms? What is it gonna do?
It's gonna pretty much just replace the oxygen, take a double bond, and don't forget that you have a ethyl group
Yep,
on it.
forms the imine. Nucleophile,
The HOCH3,
electrophile.
the carbonyl.
Does it have a heteroatom off of it?
No.
No.
So when an alcohol adds into a carbonyl without a heteroatom, what do I get?
You said when the alcohol adds into the what? What do you get?
When an alcohol adds into a carbonyl without heteroatoms, what do you get?
Um, the two oxygens, like the X shape, but one of the parts of the X is just gonna be a hydrogen.
Yeah, it's called an acetal. You get
Acetal.
double addition of your alcohol. Nucleophile,
The Grignard.
Grignard, electrophile. Does it have a carbonyl or a heteroatom on it?
No.
No.
No. So when it adds, it just adds once. Carbon just adds once. We're here. Nucleophile is diethylamine. Electrophile is this. Carbonyl. Does it have a heteroatom on it?
No. Mm.
No. So when nitrogens add into carbonyls without heteroatoms, what do I get?
Um,
It's gonna look the same, just with the nitrogen where the oxygen is, but this time, you can't have a double bond connecting the nitrogen. You're gonna push the double bond down because it's
You actually
NHR2
push it up.
up.
Yeah, to satisfy the positive charge. Can you see my mouse?
Oh, that's what I meant. That's what I meant. Yeah, you push it up.
Yeah, and you form the enamine. So you draw the imine, you say, wait, this nitrogen has 4 bonds on it, it's positively charged, so I have to form the enamine.
Yes.
Okay, so that was one class. I guess we did, yeah. All right, so this is where I lost you guys, I think.
I agree.
Yeah, I agree too.
All right, my electrophile is a carbonyl with a heteroatom on it. So what can I do to get from here to here?
Alcohol attacks carbonyl.
Yeah, I need to substitute. What do I need to substitute this methanol with?
The entire
Uh, see this part?
You use the NaOH to substitute it?
Yes, the OH is my nucleophile. It substitutes that out to give me this.
Can
Right?
you draw the mechanism for that?
I have to go. Thank you so much, Kevin.
Yeah, I hope I helped.
You did.
This is so jank. That's mechanism. You're just substituting this part for this part.
Yeah, I got it. It just helps now that I've seen it, it's like it makes so much more sense.
Yeah, yeah, no, good. I'm glad that you're filtering through mechanisms. All right. Again, I've got a carbonyl with a heteroatom off of it. So I can substitute that out. What do I want to substitute it out with? Essentially, I'm going to redraw this group. And to be honest, you're just safe. You're safe with any sort of acidic conditions. Acidic conditions are safer than basic conditions.
Do you want us to write the acid or can we just write the top part?
I'll probably say like H2SO4 and then leave a blank here.
Okay.
Yeah. In theory, this would also work in basic conditions. You could do a deprotonated amine. But what I want you to see is that you're just substituting this O for this N ethyl. And that O still has to be attached. All right, here's a Grignard addition, but because there's a leaving group, Grignards add twice. You reform a carbonyl and a Grignard's going to add a second time.
Do we need to know that even if you don't put two equivalents?
I'll probably be nice.
Okay, awesome.
Or I might just say excess. That would be a way that I could test you while still trying to remind you that, hey, something else happened.
Yeah, Zach told me that excess means the same thing.
Excess just means you have way too much.
Yeah.
Could be anything more than one. All right, so this was me throwing in a substitution reaction. So now instead of adding to the carbon in all of these reactions, I'm adding to a carbonyl carbon, but now I'm building off of this oxygen. And if the oxygen's going to be if this oxygen's going to be a partner in a reaction, it's got to be a nucleophile. That means I need to pair it with an electrophile. So I just chose something with a leaving group. This is a substitution reaction from day one. Not day one, but from last test. All right, I think people got the LAH and the PCC pretty well. Oxidation reduction. All right, this is the opposite of what we were talking about earlier. Where now I'm replacing this with this. So I need to somehow have a group with a methyl and an oxygen. But here's the trick, and this kind of goes back to one of the tests we were looking at. If you do this in basic conditions, if you have this, what is it going to do? This is essentially OMe minus.
It would attack the carbonyl normally.
It would normally attack the carbonyl, except this isn't a normal carbonyl.
It's a carboxylic acid and a base. You said it's basic conditions, so a base wouldn't act like a nucleophile. It would act like a base and take the proton, right?
Yeah.
Yes. So it would take the proton and we'd never get addition into this carbon. So that's why I say the acidic conditions are safer. Because you don't have to worry about deprotonating a carboxylic acid. Because if you deprotonate a carboxylic acid, you're done. It's over. Something also interesting is you could deprotonate this carboxylic acid with a base. If you wanted to do it in basic conditions, carboxylic acids are kind of cool. Because what is this?
That's a nucleophile?
So could you pair it with some electrophile to add a carbon?
Yeah.
Like what?
Like another, well, you could do, if you just wanted to add like one, you could pair it with a halogen.
So like a methyl iodide.
Yeah.
Yep, that will do it. So in acidic conditions, this acts like a nucleophile. Or sorry, in acidic conditions, this acts like an electrophile, but in basic conditions, it can act like a nucleophile. So carboxylic acids are a little funny like that. Um,
I need to go, but
yeah.
I'll see you guys tomorrow. I mean,
All right. See you, Margo.
see ya.
Yeah.
All right, Evelyn. Is there any other like particular questions you have? Like anyone that gave you tricks?
Um, Sorry, if I'm holding you like past the time that you need to leave, it's like okay.
No, it's fine. I got a few more minutes.
There's just I found the one where it's like MEO and then the one right under it were the last two that were really confusing to me.
Where?
It was like on the page you're just it's right there. Like those two, the MEO one, OH, sorry.
Yeah. I've got a carbonyl. Does it have a heteroatom on it?
No.
What happens when oxygen nucleophiles add to a carbonyl without heteroatom?
It would just push up, like it would push up the electrons and make that oxygen negatively charged.
Okay. I mean, it's in acidic conditions, but this is where you have to do a little bit of memorization.
Mhm.
If an alcohol adds into a carbonyl without a heteroatom, it's going to end up adding twice.
Okay.
So you end up forming what's called an acetal,
Okay.
where this methanol has added twice to the carbonyl. Every time. Every time an alcohol nucleophile adds into a carbonyl without a heteroatom, it will add twice. We call that an acetal.
Gotcha. But wouldn't that mean that would that oxygen that was in the original carbonyl, would that eventually end up leaving, like acting as a leaving group?
It leaves as water eventually. So yes, it does. Yeah, this oxygen has to be replaced.
Okay.
Um, yeah, so this one was a little bit tricky. So you see that this group is part of the final product. So I had to have substituted it out, which meant that I had a carbonyl with some sort of leaving group on it. And I can tell based off of HCl that Cl had to have been my leaving group. I balanced the equation out.
Gotcha. And it's because the alcohol there would attack the carbonyl and the wait, no, it wouldn't. It would just go into the middle and then the
So you push it up and then it comes back down and kicks off the chlorine as a
oh god.
leaving group.
Okay, that makes more sense now.
Yeah, it's kind of hard to think about these backwards, but uh here's my bad notes. No heteroatom off of this carbonyl. So when a nitrogen attacks, I form an imine.
Yeah.
But this imine's positively charged, so I have to form the enamine.
Yeah. That one, those ones like make sense. But some of the other ones I was just confusing myself.
Like here. Now it's the same question, but there's a heteroatom.
Yeah.
So when I add, I don't form an imine. I do a substitution of this alcohol.
Okay. So any single time there's a heteroatom, you're substituting rather than like adding it to.
Yes.
Okay.
But this OH, this oxygen still is attached to this chain. So you've got to draw it.
Yeah.
Um, this one's straightforward. It's just a Grignard. Um,
Yeah, and the LAH, that one makes sense too. That one makes sense.
yeah, and then we'll talk more about synthesis.
Yeah, the synthesis isn't too bad. It's not like
For you, maybe.
yeah, I know, I know. Okay. Thank you so much. I really appreciate it.
Yeah, no, thanks for hopping on, and hopefully this will be useful for other people. But it's 2 hours, so I don't know how many people are actually gonna watch it. But if you made it through, let me know
All
in
right.
class on Friday. Besides you, Evelyn, I know you made it. All right. Well, I'm gonna stop recording.